Thanks for the introduction, Larry, and I'm glad some people are sticking with us tonight at this rather late hour to hear about what we're doing. Luckily, some of the things that I'm going to say have already been said in the afternoon, so I can go quickly on some things. And yes, so this is the starting point. We do research in solution process solar cells. And the challenge that we face every day is that we somehow need to go from a few material combinations that we have in the end, ideally, to some device and product. And in order to go through this process, we have to bridge the microscale to go through the mesoscale, the macro scale, and everywhere there are things that happen. There are many parameters that influence the properties of these devices at all these length scales. And in order to do an exhaustive study of this, we would have to create many layers and devices and do many experiments that we can never cover in the laboratory. So and ideally, what we would like to have is something that really takes us from the micro scale all the way up to the final product. We would like to have descriptors that tell us how things work in the end so that we don't have to do all these experiments. Where we come from, our domain knowledge is photovoltaics. And what we're trying to do is to bring this domain knowledge and fuse it with something that I call Lab 4.0. So things that we know from the Industry 4.0, the automation part, dealing with data, databases, artificial intelligence. We want to utilize these things in order to enhance our domain knowledge and get quicker to the answers that we actually are looking for. And we want to generate high quality data sets, and then we want to use machine learning in order to analyze these, in order to supplement what we can do in the lab. The strategy that we're following here is to create data models and manage data, create structured data, then have artificial intelligence, machine learning methods and models that we can apply. And in the end, we also need tools that generate data that allow us to actually do the experiments and test these approaches that we have developed. We think that this is a process that we can apply to many fields of material science. We think we need to find ways to incorporate as much of existing knowledge as possible. Then we think that we can actually utilize something like a self-driven laboratory, ideally even a distributed laboratory that couples together many pieces of equipment. Then this is a generic approach, and we think that it can actually accelerate material science by a factor of 10. And what we want to do is use these methods and demonstrate it at the hand of solution processed photovoltaics. So what we have done in our laboratory is that we have developed along this line, going from synthesis all the way to aging, methods that automate various processes that are going on. This starts on the synthesis end, where we start with microwave reactors that allow us to do simple coupling reactions and give us access to material libraries of our own. We have done a lot of work in the formulation part, using pipetting robots that allow us to do combinatorial mixing, or also simple synthesis methods that we can do in solution. But we can also use these in order to create sort of simple or crude films by drop casting. Then we want to go on, we want to have higher quality films because we're interested in the solid state properties. Of course, for this, we've developed our so-called spin bots that allow us to use spin coating, which we've identified as a great method in order to work with these materials to do discrete experiments that are really separate from each other and allow us to probe large parts of the parameter spaces. We go on to the automated manufacturing of full devices and characterizing them in line with various methods. And we've even added in some accelerated lifetime testing that allow us to do inline lifetime testing, which has to be somewhat quick, but we can also take it offline if we want to investigate these materials for a longer time, run longer experiments, and test them there. The tools that we've developed really are grouped around 3 platforms. And I'll tell you in the talk a little bit about this platform. One is more or less a store-bought pipetting robot. Then we have these so-called spin-bot platforms, which I'll go into a little more detail. And then a larger system that we call line 1, which actually goes from the solution all the way to the full device and the stability testing, and allows us to run the whole process fully automated. Let me start with this TECAN system here and its capabilities. So you're getting a close-up look at the system. At the heart of it are these pipetting channels that you see here. It has 4 channels that allow us to aspirate solutions and dispense them, of course. It draws tips from this repository here. Then we have master solutions where we can actually take stock solutions that we then mix together in certain samples, where we often work with weld plates. You would place them over here. Then we can heat the solutions, we can shake the solutions to do various operations on them. And in the end, we can also characterize them as libraries in this UV-Vis photoluminescence plate reader. Let me give you a little bit of an impression what this looks like. Here you see a movie. It's sped up so it doesn't take so long. This is a synthesis reaction that we are running for lead-free nanoparticles, lead-free perovskite nanoparticles that in the end we will have in a suspension. Over you see that we have 3 components, A, B, C, referring to the ABX3 structure that we are mixing together in various combinatorial combinations. Then we do a second set of master solutions, which we will now pipette into each other. And as we do that, the reaction will start, and we will actually start, and perovskites will start falling out. Up front here, you will see there is a suspension. You see actually there's some white parts. Now with the pipetting tips, we can pipette them up, and we can do a drop casting in order to prepare some films that we can then either analyze with UV-Vis or here, just so we see some of the differences. So with such an approach, we have a very highly precise method of creating many samples per day. And it's a way of allowing us to create relatively large and finely spaced libraries with high precision and reproducibility. Then we take these and we've built systems around it that allow us to actually measure these libraries. The UV-Vis absorption spectrometer you already saw, but we also have the option of doing a Raman investigation or time-resolved photoluminescence measurements, allowing us to characterize various properties of a semiconductor that we ultimately would like to see in the end, of course. And when we do this right, with such a method, we have ways of really scanning in very fine detail large parameter spaces. For example, here we're showing how to vary across 4 orders of magnitude the bismuth fraction in these can-bake lead-free perovskites. And actually where we're seeing rather large lifetimes, PL lifetimes here on the order of microseconds, and we're seeing extremely high photoluminescent quantum yields of almost 100%. There are many more things that you can do with this. So we're also interested, of course, in the application of machine learning. Here's an example of a relatively early experiment where we exploit similar capabilities as in the video that you saw before. In this case, we are looking at ternary combinations or quaternary combinations of organic photovoltaic materials that we are mixing together with a simple question. And the question is, where do we find the highest light stability of these quaternary mixtures? And what does it take to actually find this most stable combination? So what you're seeing is this combinatorial mixing of many different concentration variations that we have. Then we take these mixtures, we drop cast them again in order to create a film. Down here you see the fresh samples. We take these samples, we expose them to one sun, illumination in oxygen or in a regular air atmosphere, age the samples for 24 hours. look at them again with the absorption, and from that we can characterize a rather simple stability criterion for these. The smaller the changes, the more stable these materials are. And as you see this, you get sort of like a pyramid parameter space. And if you want to cover this full parameter space in something, say like 10% steps, you end up that you have to make 1,000 samples. This is, of course, challenging, even with the methods that we're showing. So what we wanted to know in this particular experiment was, can we actually speed up this, or can we work with less samples if we use artificial intelligence, and how much or how well can this AI actually predict what is happening here? So we included a Bayesian optimizer working together with the Matter Lab at the University of Toronto, and actually Loic, which we heard earlier today. And we could show that rather than needing 1,000 samples, we could actually, with this approach, predict the same composition with roughly 60 samples. So we had about a 20x improvement in the number of samples that we need, and of course much lower materials usage, as we have already seen in the first talk of the session today. So going on from there, we would like to do, of course, more precise film generation that allow us to do higher quality films. And we would like to move on to the spin coating. For this, we developed a fully automated spin coating platform, the platform we call a SpinBot. What you're seeing here is a SCARA robot. This allows us to move in the X, Y, and Z direction on this work platform here. It includes a gripper, allowing us to manipulate samples. It has a pipetting channel that allows us to aspirate and dispense solutions. And it has a spin coater here on the left. Now in this movie, you see how this is working. We always like to work in these what we call carriers, these trays that hold 8 samples. Then we can stack these carriers. In the first step, you saw the gripper pick up one of these carriers, and we took out a sample, placed it on the spin coater. Now you've seen the actual spin coating step. You saw the drying in there. Then we're depositing the sample back. We can ablate some of the polymer film, because in order to make cells, we actually need to uncover the ITO that is below. We can anneal the films. And then when we're done with the full process, we more or less place the carrier in the outbox and then start over with the next carrier. By doing this, we can process about 100 discrete samples in one session, with each having individual parameters for the actual, for the sample preparation, for the annealing, for the mixture that is used, highly individualized on the sample level. When you have this capability, there are many things that you can do, particularly in the perovskite space. This is highly interesting. Here's an example of cation engineering that we've done. Over here, you see the ABX3 structure. Then at the A cation side, we actually varied from several organic and inorganic cations that we used in various mixtures. We created a matrix of films and then exposed this matrix, these films that we generated to various accelerated aging conditions, elevated temperatures per se, and then investigated via measurements like photoluminescence, the aging behavior of these films, and could identify which of these molecules are actually leading to more stable and to less stable perovskites at these different conditions. Then once you have this, you can actually take it further. So here's an example of how we can go through a selection and screening process for stable perovskite compositions. Obviously, there's too much data here to go through it in all detail, but we started out with 160 compositions, and by screening which compositions actually form a black phase, which compositions remain stable when exposed to high temperatures, which have the best photoluminescent properties. We could then screen out just a handful of highly promising perovskite compositions, down select, and with these promising conditions actually go through and then manufacture devices. That, unfortunately, is not enough. We still have to put in quite a bit of device engineering, device architecture development. In this case, in particular, we had to work on the top electrode, which was another source of degradation. So we stabilized the actual active layer for light absorption, but we still needed to stabilize the interface to the electrode. But once we've done that and brought it all together, you can see we could actually demonstrate very, very stable perovskite cells that lasted at elevated temperatures and roughly 1 sun illumination for 1400 hours without showing any degradation at all. So we can make highly stable perovskites in this fashion. The next step for us from there is to go fully automated from the material mixing all the way to a full device and a stability testing. And that's what we've put together in this machine here, the platform line 1. Line 1 consists of this somewhat impressive control desk with lots of monitors, allowing us to monitor everything that is going on. It has a glove box for solution preparation where we make master solutions that we will then use for the device manufacturing. We can process thin films. This is done again by spin coating. We can do characterization steps. We take photos of all the films. We do UV vis absorption. Then we can evaporate on a back electrode. We can do the JV characterization over here. And finally, we can do accelerated stability testing by exposing it to light at elevated temperatures and seeing how they degrade over time. So just to give you a little bit of an impression of what this looks like when you do it, we developed a software platform around it that allows us to actually input the architecture, a device architecture builder. Then we have the spin coater here creating the layers. Again, the ablation that you saw earlier for the spin bot. In this machine, we pass on the carriers from one station to the next fully automatically. You saw the JV characterization, now the control mechanisms for the instruments. So this is a rather complex machinery that is gone from a simple automation of a few steps to the full orchestration of many pieces of automated equipment in order to run a large-scale design of experiment. In the beginning, all of this is tied together by a software platform, the Amanda platform. You already saw a little bit of a glimpse. There's a graphical user interface with a device builder or a process builder that you can simply use by drag and drop. All of this, all these interfaces are through our browser interfaces, so you can actually run this and do your designs of experiments for anywhere. Then we have a software in the middle that allows us to control all the pieces of equipment that we have. It does the orchestration that I mentioned of these various equipments. It sends the commands, it reads back the data, outputs the data into the database, and allows us to control centrally at once multiple hardware materials acceleration platforms. And these are the platforms that you've already seen. And of course, most important, it outputs everything into a database and consolidates all the things that are happening in there. This data is then accessible through an API for further analysis. The types of data that we take, you can see here. Here you see a product, as we call it, with various pieces of information that are available for this product, which include an image, absorption spectra. We have 6 cells on each of the substrates typically, and we take 1 absorption spectrum at each center for these cells. We take JV curves at various light intensities, and then we measure the stability, where we measure the performance at various intervals throughout the testing cycle. In this particular case, that was roughly 30 hours, but at about 10 suns. So you get out to about 300 sun hours in something like a day. Very important to us because the next day we of course want to run the next experiment. All the data, relevant data, is collected in an SQL database. Right now we have more than 10,000 samples, roughly 60,000 measurements. So we're getting to the 10 to the 5 number that we already heard several times today. And of course, on top of that, we have all the metadata from the production of these devices. We collect everything that happens in these events, as we call them. For example, anytime we manipulate something, we collect all the information for the spin coding, all the equipment configuration, data, user interaction loggers, etc. With the database, we can then, of course, do evaluations of the data. This is a rather simple one, just efficiency as a function of sample number, but we can also investigate structure property relationships. So this is some work that Larry already described in detail, so I'm not going to go into this anymore, but the important part is we can now essentially the word transfer learning was already mentioned earlier. This is something that we can apply here. We learned how to use the spectra from our absorption in order to predict device properties before we actually make them. We have a reasonable efficiency for that, and this is something that we can already use in order to enhance and speed up the process for the development of these solar cells. This is something that is actually very interesting to us, because the next step is, of course, to integrate it and to go from this automated processing to an autonomous processing. Here's an example of that, where we've taken the data that we collected, read it out, then use a Bayesian optimizer in order to tell us which samples to do next. We do batches of 6 substrates each, so we process 6 substrates at certain conditions. We measure them, or we predict their performance if we don't have measurements yet. And from this data, we have a Bayesian optimizer tell us actually what are the next 6 substrates that we should make in order to approach a certain criteria for performance and or a certain objective. In this case, it was a multi-objective optimization in 3 dimensions of a ternary combination, quaternary combination of materials. And what you see in here is the batch number, and then the efficiency and the stability. And what you're seeing is that it takes us about 9 iterations, and after that, it stabilizes. So with roughly 60 samples, we could actually find the optimum, which is rather quick. And we also tried around this optimum to see how robust this was by manually iterating around it, and we could not find anything better than this algorithm. So it's reliable. Next thing is to push the boundaries of the number of dimensions where you optimize in. Last one was multi-objective 3 dimensions. This is a 4-dimensional optimization. Here it's a ternary, but we also allowed for variation of processing conditions, in this case, the spin speed. And again, what you see is that here we see the cell number or the batch number, and then the convergence to the objective. And in this case, already after about 6 iterations, we found the optimum. Here in this projection, you can kind of see how the algorithm actually picks its points. First, it scans the space, then it finds promising areas in the space, and it puts more points around it, and then identifies the optimum in this way. How well does it work? It actually works rather well. So we tried it once manually, where we could get to roughly 13%, and we found the expected result that we would do better in the ternary. The optimizer actually managed to get to 14% in the ternary, and to us, somewhat surprising, found an optimum, though, in the binary mixture and not the ternary mixture. So we found an unexpected optimum, and we find this rather exciting. Let me put it this way. So where are we at? This is kind of where we started out 5 years ago. This is actually a very old plot. The idea was to create this automated platform that allows us to do all this. This is something we have today. We can couple in machine learning. We have our external data grid. We're starting to work on this quantum chemical simulation and the synthesis. So this is what's in the future. The ML, we're going to improve, increase the dimensions, improve the way that we couple it into the systems. We see a lot of work ahead of us on the data structure, databases, ontologies. Right now, we have a database that's only internally for us. We want to be able to actually have a database that spans all Helmholtz Society, allowing us to share data. We are starting or increasing our efforts in the high throughput synthesis area. We're also working here with Pascal Friedrich and allowing us to do a machine learning guided selection of these materials, which is also very exciting. And ultimately, of course, we would like to scan have the whole pipeline from the material synthesis all the way to the final devices in one run. With this, I thank you for listening. I hope I convinced you that automation is a good way of improving precision and reproducibility. The power of ML in this is something that we're learning more and more about, and that we're learning about how to apply it in more efficient ways. A database is something extremely important because it also allows us to go into the reuse of data and the data sharing. We believe that high quality data sets are going to be extremely important. And yeah, we're more and more using this in order to address and solve relevant questions and accelerate materials discovery. With this, of course, there's a lot of people behind this that have contributed here. There are also people that fund us, and we thank those for this. And with this, I'm open for questions. Thanks.